How do you evaluate the performance of your model? Well, the first metric you can look at is accuracy. And accuracy is the fraction of predictions our model gets right. And formally, accuracy has a definition like this. Accuracy equals number of correct predictions over the total number of predictions. So, for example, if we had a model that was trying to identify tumors and we had 100 images and we were classifying whether that image shows a malignant tumor or a benign tumor, and let's say our accuracy turned out to be 0.91, then 91 of the 100 examples received correct predictions. So can we conclude that our model is performing well? Actually, let's do a closer analysis of the positives and negatives to gain more insight into our model's performance. Let's say that of the 100 tumor examples, 91 are benign and 9 are malignant. And of the 91 benign tumors, the model correctly identified 90 as benign, which is good. However, of the 9 malignant tumors, the model only correctly identified 1 as malignant, which is then a terrible outcome because 8 of the 9 malignancies went undiagnosed. And so while the 91% accuracy may seem good at first glance, if we had another tumor classifier model that simply always predicts benign for every example it receives, well, that model would perform equally well because it would also score 91 out of 100. 91 of the tumor examples are benign, and the model we've created would be no better than that one because it would have zero predictive ability to distinguish malignant tumors from the benign tumors. And so accuracy alone does not really tell the full picture when you're working with class imbalanced data sets like this one, where one class of the data set is disproportionately larger than the other class. In this case, the benign tumors will represent the majority of the data in our data set, and the malignant tumors would represent a very small minority. And so we have to rely on something other than just accuracy. And this is where we look at the confusion matrix. So what is a confusion matrix and why do you need it? Well, it is a performance measurement for machine learning classification problems where your output can be 2 or more classes. And in this table below, you can see the 4 different combinations of predicted and actual values that are possible. You have TP, which is true positive, and FP, false positive, and then you have false negative and true negative. So let's first start off by looking at understanding these concepts. Let's examine it in terms of a pregnancy analogy. So here's a confusion matrix showing the predicted values and actual values using a pregnancy example. So in this scenario, your true positive means that you predicted positively and it's true because you predicted that a woman is pregnant and she actually is. And then with the true negative, which is on the bottom right, you predicted negatively and it's true. So you predicted that the man is not pregnant and he actually is not. So that's an example of true negative. And then false positive, which is also called a type 1 error, is where you predicted positively and it's false. So here you've predicted that the man is pregnant, but he actually is not. So that's false positive. And then the false negative is on the bottom left, and you've predicted negatively and it's false. So you predicted that the woman is not pregnant, but she actually is. So in summary, when you look at this word true positive, what you'll notice is that the first word is looking at the actual value, and that can be described as true or false. And then the second word is looking at the predicted value, which is positive or negative. So we could draw it out like this to show that the first word asks the question, was the prediction right? And the second word asks the question, what was predicted by the model? Okay, in our next lesson, we will look at some of the metrics that can be computed from a confusion matrix. See you soon.